like it. So these are the areas we're going to look at today. Explain what a model is, identify 3 types of models that scientists use, outline different models and explain why they're useful, outline the particle model, so we're using that to explain the properties of substances, and then using that to explain the effect of heat on different states of matter, and lastly using it to explain that why different substances have different melting, boiling and freezing points. So scientific models, the reason why we use them is kind of to simplify what's happening in reality to something in which we can explore, we can measure, and becomes more easier to explain, right? It simplifies what's happening in reality into almost a simulation that allows us to observe and explain things. Yeah? So a model isn't the real thing. A model is a representation of the real thing. They're really useful, and we're often updating our model as new bits of evidence come in. So if we look at the atomic model, which is one example, we've got things like the climate model. So we're observing, we're collecting data and using the model to make predictions about our future. The future looks pretty grim as far as climate change goes. We have the atomic model. And what I've displayed here on the right-hand side is an illustration to show that models are not constant. Models change over time as new bits of evidence come into play. So in 1803, right, John Dalton came up with this idea of this solid ball. So this solid sphere of particles all joined together. 100 years later, Thomson came up with this idea of the fluid model. A sphere with raisins or crumbs in it, illustrating that atoms have charge. 7 years later, Rutherford came along and discovered the fact that atoms are actually mostly empty space. They did this famous what's called gold foil experiment. We fired some radioactive particles through very thin foil, and most of them went through. Some of them deflected or bounced back at wide angles. And it was that wide angles and deflection that he realized there's something hard and small in the center. What we now know as the nucleus. That's the nuclear model. A few more years later, Bohr came by and discovered the fact that, well, these electrons aren't just spinning around, but they occupy specific levels of energy. And we can test this using flame tests by placing metals in the flame test, and we can observe that different metals are different colors. And then lastly, that's depicted there is quantum mechanics from the 1930s, right? It's just, again, this elaboration of this idea that electrons occupy regions of space. Yeah? And even as late as 2012, so another 100 years later, we're discovering more and more parts of the atom, thanks to the Large Hadron Collider, splitting apart and breaking apart atoms into different pieces. We've got the cell model. It's a model in which we can identify and look at particular parts of the cell. The cell is the building block of all life on the planet. The plant and animal models. And we look at the cell in Year 8 science. Most importantly for this unit is looking at the particle model. So the term particle in science was used to simply describe a very small piece of matter, right? The general term. Particles could be atoms, particles could be molecules, particles could be ions, particles could be a piece of substance. Yeah? It's a general term to describe a small piece of substance. And they're not all the same. Some are big, some are small. Right? So we can use this model to describe the different states of matter: solid, liquid, gas, and main states of matter. We are solid. We have blood moving around us in our body. That's a liquid. We're breathing in and out of gas. So solids, the particles are tightly packed together. They have a low amount of energy. But they're not, the particles aren't stationary. The particles vibrate. They don't have a tuning fork. But if you notice, when you tap on a table, the table ever so slightly vibrates. Or if you get one person at one end of the table, you put your ear against the table and Tess taps on the table, you can hear it. And that's because the energy, right, of the tapping of the table is transferring through those vibrations on the table, right? And it's actually traveling faster through the table than it is through the air. Solids have a fixed shape. What does the word fixed mean? Yeah. No, it doesn't change. So solids have a fixed shape. It does not change its shape. And they have a fixed volume. Volume is the capacity of which it occupies in space. Yeah. So my mug is 300 ml of volume. My mug's a solid. I can put liquid in it, but it's a solid. Fixed volume and a fixed shape. In a liquid, particles are still close, but they have higher energy. They're moving. They're rolling over one another. Liquids and gases alike are known as a fluid. Fluid substances are substances that flow. They can pour. Yeah? They can change shape, and the shape in which they occupy fills the container in which they are in. So if I take Yeshin's drink bottle, right, and notice how the volume occupies in this shape, I tilt it on its side, the volume hasn't changed, but the shape of the liquid has. Yeah? Because the shape of the liquid occupies the shape of the container in which it's in. In this fashion, it occupies that shape. In this coordination, it occupies a different shape. That make sense? Yeah. In this, it occupies another different shape, but I'm not changing the volume. In a gas, energy is faster again. They have lots of energy. They move around. They don't stick together very easily, unlike liquids and solids. Liquids and solids, they're stuck together quite well. Gases can change their shape and their volume. I can breathe into here, increase the amount of particles in that space. I can breathe out. Okay, I'm changing the number of particles in the space. I can breathe something. I'm changing the number of particles in the volume of this. Not changing the volume, but so gases occupy the entire volume of the container. Yeah? So if I was to seal the doors and suck out all the air, the volume of this room would change. Yeah? You would all die, but we wouldn't want that. Or the reverse is I can seal the container and pump more gas in. Yeah? Increase the pressure of the room. Boost the amount of oxygen in the room. Yeah? So when you think about inflating your car or your bicycle tires, as you put more gas in, it's changing the shape and changing the volume of the container, right? And the tire essentially is a container. So it fills up the container in which it's in. When I take a solid and I start to heat it, you see. I'm going to take a solid and I apply some heat to it. What's happening is that the particles move slightly away from one another. So even in a solid, we still have some small amount of space in between particles. As I increase the temperature, as the diagram indicates, is that as I increase the temperature, the space in between particles increases. The particles themselves don't change size. It's the space in between them that changes size. I'm giving those particles more and more energy. As I continue to give it more energy, that will continue to expand. And we can see that the vibration of those particles moves more and more rapidly. Let's go laser pointer. Yeah, I can see that they move more and more rapidly, and the volume in which they occupy starts to increase. And then eventually, right, I've given it enough energy that it will break entirely and those particles will start to roll over one another and become a liquid. And so that process is called melting. Yeah? We know what melting looks like. Everyone's eaten an ice cream, I'm sure, on a hot day. The ice cream, semi-solid, melts into a liquid and you get sticky hands.
Yeah,
Ice goes into a liquid, then continue to boil, it goes into a gas.
Let's say there's a hamburger. If you overheat it, it will get burnt.
Right, that's a chemical reaction. That's a thermal decomposition. So you're actually boiling off the water, and the other components remaining in the burger are undergoing a thermal decomposition. So you're breaking down some of the chemicals within the burger into carbon, which is why it's black, and then the other components are vaporizing up. So it's different to heating and melting. Yeah. Yeah.
Why did it like solve?
So if you've got pasta, for example, that's because of the starch that breaks down and dissolves into the water, traps some of the air, traps some of the gaseous water as a bubble, and that's why it foams over. If you had pure water, it would just boil. Some of the water is recondensing on the outside. So it's boiling and then recondensing back to water again. Cool. All right. Thank you. Couple more minutes. Yeah? Thank you for your attention. You've been really attentive. Let's see if you can give me 2 more minutes. Do you think you can do that? Yeah. So we give a liquid more and more energy, same idea. The liquid expands. As we're giving those particles more and more energy, the space between them increases. Eventually, we've given it enough energy such that the particles will move into a gaseous state. Or the reverse. Take a liquid and remove the energy from it. Particles condense. The space between particles becomes smaller and it freezes. And there's an Easter egg about the snowflakes, and there's some information about that in the notes. Encourage you to look at that. Question?
If you put water in a bottle, then you freeze it.
Yep.
For some reason,
yes, water is a very unique substance in that water expands because of the way in which the water particles align themselves. So they align themselves in this hexagonal structure, and air, right, and its space, the way in which they align themselves when they freeze, is such that water will expand when frozen. Most substances won't do that. Water's unique. 1 more minute. Okay, little bit of extension. If I take a gas and heat it up even further, we can get what's called plasma. Right? If I take a really, really cold gas and cool it even further, we can get what's called Bose-Einstein condensates. Another unique state of matter. And those of you who are interested, I'll talk about that another day. There's a little video about heating up a gas. We can see what is happening with the particles that are in it as the temperature increases. Particles move more rapidly. Cool a gas and eventually it will condense back to a liquid. All right. Now, when we had the dry ice demonstrations, dry ice is called dry because it doesn't have a liquid phase. It goes straight from a solid to a liquid, from a solid to a gas. And that process is called sublimation. If I do the reverse, bypass the liquid phase when cooling, we get deposition. And this is one way in which we can make dry ice is using a fire extinguisher. Yes, sir.
What would happen if what I understand, I'm saying, was basically was put in the center.
As plasma. Well, unlikely, because they're operating at very different temperatures. Plasma's at 1,000,000 degrees, right? Or less than that, depending on the gas. Bose-Einstein condensate is very close to absolute zero. So you're not going to be able to physically go, I'm going to just pick this up and place it into this different environment. We've gotten pretty close. All right, I might leave it there. There's a summary, states of matter. 3 more slides, can we do that? Yeah? Yeah? Happy? It's Easter, so I've got a little Easter bunny with an Easter egg.
Albeit dying.
Yeah. So chocolate is really interesting. Yeah? Chocolate is this crystalline structure. Beautiful. Yeah. And chocolate melts at about 35 degrees, which is why, really good chocolate melts in your mouth as you eat it. But melts in your hand if you hold chocolate for too long. Yeah, we've got 2 more slides.
I still see worry.
And have you ever had chocolate whereby it's melted and allowed to refreeze? You notice it goes white.
Yeah.
It's called blooming. What's happening is the fat is separating from the sugar because the fat has a lower melting point than the sugar, right? So the fat, actually, chocolate really is a mixture. Yeah, and it's as it melts and re-solidifies, if you're not continuing to mix it, the fat will separate from the rest of it. Essentially, the argument on this page is that, here we go. One more slide. Thank you for your patience. I know this has been a long time. Yeah, the strength of the bond, the strength of the attraction between particles links with the higher or the lower the melting point. Last slide. There's some examples of low and high melting points. Have a wonderful break. Take care.